Today, I'm going to talk about mathematical groups. In mathematics, a group is a set of numbers that undergo an operation, such that the set is closed, associative, has an identity, and has an inverse. Before I get to these four qualifications, I should first discuss what sets and operations are. A set is really just a bunch of numbers. For example, the numbers 2, 3, 4, and 5 form a set. The numbers 1, 7, -12, 3/4, and 976 forms another set, as do the numbers pi, radical 2, -112, 36, and the imaginary number I. The size of the set and specific numbers it contains can be completely arbitrary. The only qualification for a set is that it includes some amount of numbers. Now, while sets can be arbitrary, we often care about sets that aren't. For example, an important set is the set of integers. These include positive and negative whole numbers, such as 0, 1, 2, 3, 4, and so on off to infinity, as well as -1, -2, -3, and so on off to negative infinity. Another important set is the rational numbers. These are the integers, but including fractions. So now we include 1/3, 1/2, 4/5, 13/3, as well as -1/3, -1/2, -4/5, -13/3, and so on. Really just any fraction going from negative infinity to positive infinity. But that is what a set is, some possibly infinite amount of numbers. The other part of a possible group is an operation. An operation is just a mathematical process that can be exerted on numbers, such as addition, multiplication, taking things to a power, and so on. The combination of these two, a set of numbers and an operation, forms a potential group. Note that a set of numbers and an operation alone aren't enough to define a group. It also needs to be closed, associative, have an identity, and have an inverse. I'm going to start with the closed qualification. Being closed means that when the operation is performed between any two numbers in the set, the result is another number in the set. For example, if our set is 1, 2, and 3, and our operation is addition, we can perform the operation between the numbers 1 and 2. From this, we get the number 3, which is in the set. However, for a set to be closed, it has to be closed in every situation. So, if we add the numbers 1 and 3, we get 4, which is not in the set. As such, our set 1, 2, and 3, under the operation of addition, is not closed. So, it is not a group. For this reason, most sets that form groups are infinite. An example of such a set would be the integers under addition. Finite closed sets exist, such as with modular operations, but that's not something I'm going to get into. Again, for a set to be closed, the operation performed between any two numbers in the set has to give another number in the set. A group also needs to be associative. This means that the order in which we perform multiple instances of an operation on several numbers does not matter. For example, if our operation is addition, this means that adding 1 and 2 and then adding 3 is the same as adding 2 and 3 and then adding 1. In the first case, we get 3 plus 3, which then gives us 6. In the second, we get 1 plus 5, which also gives us 6. Since we get the same number, we see that addition is associative. Multiplication is also associative. The order in which you multiply several numbers does not matter. Something that is not associative is division. If we want to divide 54 by 9 and 3, the order matters. If we first divide 54 by 9, we get 6. Then dividing this by 3, we get 2. However, if we first divide 9 by 3, we get 3. If we then divide 54 by this, we get 18. Clearly, 18 is not equal to 2, so division is not associative. Associativity requires that the order does not matter when multiple instances of an operation are applied. The next qualification is that the set, and more so the operation, needs to have an identity. The identity is a number in the set such that an operation performed between another number in the set and the identity gives back the original number. For example, if our operation is addition, our identity would be 0. So, if we add any number, such as 3, to 0, we get back the number 3. In multiplication, the identity is 1. An example of an operation without an identity is the cross product. A cross product is a type of multiplication between vectors. A vector is some property with both a magnitude and a direction. I discuss both vectors and cross products more in a separate video. But the reason an identity doesn't exist for cross products is because the cross product between any two vectors gives a third vector perpendicular to both vectors. This means that even if some identity vector gives back the same magnitude of the original vector, this new vector will be in a different direction, so it will still be a different vector. That aside, an identity is a number included in the set that will output the same other number when the operation is performed between the identity and some other number. The last qualification a set and operation needs to meet to be considered a group is that they have to have a valid inverse. Formally, an inverse is an operation such that if it is performed between two of the same number in a set, we get the identity. More simply, the inverse is the opposite of the operation. So for addition, the inverse is subtraction. For multiplication, it is division, and so on. For the inverse to be valid, it needs to work between all numbers in a set. So if our set is the integers with the operation addition, the inverse exists. We can subtract any two integers and get back an integer. For example, 3 minus 2 is 1, which is an integer. However, if the operation is multiplication on the set of integers, we do not have a valid inverse. First off, dividing any two integers does not necessarily give us back an integer. 2 divided by 5, or 2/5, is not an integer. Furthermore, dividing any of the numbers by 0 is an invalid operation. We don't get a number back. We can fix these problems with multiplication by using the set of positive rational numbers. In this way, we include fractions, so 2/5 is now a number in a set. And by restricting the set to positive numbers, we exclude 0, so we don't get problems with dividing by 0. Again, a valid inverse is the opposite of the operation that will give us numbers included in the set. All of this tells us how to define a group. So, if we take a set with some operation that is closed, associative, has an identity, and has an inverse, we have a group. Now, as was indicated with my examples for each of the qualifications, the set of integers under the operation of addition forms a group. We have seen that it is closed, Adding any two integers gives another integer. It is associative. The order in which we add several numbers doesn't matter. It has an identity. 0 plus any integer gives back the same integer. And it has an inverse. You can subtract any two integers and still get an integer. Another group is the set of positive rational numbers under the operation of multiplication. I encourage you to check this for yourself to be sure. Now, a set and operation have to pass all four of these qualifications to be a group. If it fails any one of them, it is not a group. It should also be noted that other qualifications can be added to make specific types of groups. For example, if we require the group to also be commutative, where the operation order between two numbers doesn't matter, then we have an abelian group. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.